Okay, we're going to do a screencast of a few of the Mastering Physics problems that were due today. I'm going to do the second problem, the fourth problem, and the sixth problem that were in the assignment that was due today. I'll just review those. The second one was problem 1066, and this is out of chapter 10. And we've not really talked about torque equals I times alpha until chapter 11. So just keep that in mind as we try and figure out how to solve this problem. A block of mass M, 3.1 kilograms, that's the mass of this block right down here, is attached to a string that's wrapped around the circumference of a wheel that has a radius of 7.6 centimeters. The wheel rotates freely about its axis, and the string wraps around the circumference without slipping. Initially, the wheel rotates with an angular speed of omega, causing the block to rise with a linear speed of 0.27 meters per second. So the block is going up at 0.27 meters per second. We want to find the moment of inertia of the wheel if the block rises to a height of 6.8 centimeters before momentarily coming to rest. Okay. We know the mass of the block is 3.1 kilograms. It's going to come to rest just for a moment after rises. H equals 6.8 centimeters. I'll just turn that into meters right away, 0.068 meters. And the radius on the wheel, we're told, is 0.076 meters. Okay, so that's R. Okay, so we have some given information. When they're talking about heights and they're talking about something going from moving to not moving, you want to start thinking about conservation of energy, because you've got a bunch of energy at the beginning and you've got only gravitational energy at the end. So they're basically telling you, consider this beginning point to be y equals 0, which means that's your reference point for gravitational UG, so that's going to be 0. And the type of energy I have at the beginning, I've got some kinetic energy of translation here initially. I've got kinetic energy rotationally initially. And then at the end, the only thing I have, since neither the block is moving nor is the pulley turning anymore, I have all UG at the end, final. So I draw those circles like they're the pies, you know, like the pie is, initially you have two different kinds. Actually, I probably should have shown it like this. K rotation and K translational initial equals, you know, UG final. So that's the big idea equation for this one. Okay? So we want to calculate the moment of inertia of the wheel. So I'm going to erase all this so I have some space to work. And I'm going to move this up here. My rotational moment of inertia. Okay, so I'm going to fill in the formulas here. I've got 1/2 I omega squared. And remember, the 1/2 is in the formula. That's not part of my value of I. That's in the formula. Plus 1/2 m v squared equals mgh. Since we're trying to calculate the moment of inertia of the wheel, really, you're not going to substitute anything in for that. We're just trying to solve for I. They're asking for I in units of kilograms times meters squared. I've got my linear velocity v. My linear velocity is given, so I know this term. I know the mass of my block, which are these terms right here. I've got h, so I know that. And omega is just v over r. And that's why they gave us the radius. So if I know the rotational velocity of this wheel, then I know the instantaneous linear velocity at the rim of the wheel. If I know the radius of the wheel and I know the rate at which it's turning, I can calculate the linear velocity with the formula v translational or v tangential, same thing, equals r omega. So omega equals v over r. So I'm going to substitute that in right there. Okay? So then I'm going to have 1/2 I'll go offline. I'll do this offline and I'll come back. Okay, I've put all the numbers in for this one after we set it up. And I substituted in here for omega v over r, quantity squared. I got that again from this formula up here. And then I just rearranged up to this step right here. So I subtracted the 1/2 mv squared over to this side. That's right here. I multiplied both sides by 2. That shows up right here. And then I multiplied by the reciprocal of v over r squared. So I get r squared over v squared right here. That was a matter of just substituting numbers in. So this step right here, I kind of ran out of room over there. I substituted all the numbers in right there. And this was a calculation step right here. And my final answer was 0.310 kilograms meters squared. And that was the right answer there. Now, the big idea, again, conservation of energy, you've got to take into account your system. So our system at the beginning of the problem was the mass and the pulley. So the mass has some translational kinetic energy, the pulley has rotational kinetic energy. You cannot just consider the mass. You have to take into account that there's some kinetic energy stored in the rotation of the pulley in this problem, okay? And then you'll get the correct answer. Okay, I'm going to move on to the second problem, which was the fourth problem in the problem set, the second one for this screencast. Okay, in problem number 4, we have 3 disks that are released at the same time from the top of an inclined plane, and disk 1 has a certain mass and a certain radius. Disk 2 has the same mass, twice at the radius, so 2 times the diameter. The third mass has the same radius as the first one, but double the mass. So one's got a larger radius, one's got a larger mass, so must be a higher density material. But they're all disks, okay? And we want to see which one will finish first. We'll consider this a conservation of energy problem because you've got all UG up here and you've got all kinetic rotational plus kinetic translational down here. So if you remember the result we got from the problem the other day that we did in class where we had a sphere rolling up a ramp, we found a really interesting thing, that the height that the sphere rolled up the ramp didn't depend on some things that we might have thought that it should depend on. So for all 3 of these, the moment of inertia is 1/2 mr squared. So we're going from mgh, and we're going to 1/2 mv squared plus 1/2 I omega squared. And when you talk about who's going to win the race, it's going to be the one that has the greatest velocity at the bottom because they're all starting from 0. So the one that's going the fastest will cover the same amount of distance in the shortest amount of time. So we can answer this question by solving for v. So I'm going to go ahead and substitute in this value of I in here, and then I'm going to simplify and solve for v. So mgh equals 1/2 mv squared plus 1/2 mr squared times omega, which rather than omega, I'm going to have the term v over r for omega, because again, v equals r omega. So to substitute in for omega, I divide both sides by the r like I did in the last problem with the same variable. So that's going to be v squared over r squared here. And look what happens. The r is going to cancel out. The mass is in each term. So right away you can see that the velocity, when I solve for this in a second, will not depend either on mass or on radius. So I could go further with this, but I already know for sure that these 3 are all going to finish at the same time. I'll go ahead and simplify it at the end, but I just want to show you that regardless of mass and radius, they all finish at the same time. I'm glad that's correct. So 1/2 v squared plus 1/4 v squared, multiplying those two together, equals GH. I got rid of my M. So combine those two, I get GH equals 3/4 V squared, or V equals the square root of 4/3 GH. So it does not depend on the speed of those things. Will be the same for all three. They all start from rest. They'll all have the same speed, the same translational speed at the bottom. And it doesn't matter what their mass is. It doesn't matter what their radius is. What matters is the shape of the object. Where is the mass concentrated? And since they all have the mass distributed the same amount around their axis of rotation, because they're all disks, they will all finish at the same time. And notice again, this is a variation of the result. If it wasn't rolling at all, the speed would be 2gh. So you would assume this would be pure translation. So you would assume that it would be a little bit less than that, which 4/3 is less than 2. Some of that energy goes towards getting these things to rotate. So that seems to make sense from an answer standpoint. Okay, last one. We're going to do the 6th one in the series, which is problem 73. Okay, this is the 6th problem in the problem set that was due today. And I've written out some of the given information. You've got a 1.1 kilogram block right here that is tied to a string. Here's the string, here's the block that is wrapped around the rim of a pulley. You've got the radius of the pulley. I automatically convert that into meters from centimeters. And the block is released from rest. So initial velocity of the block is 0. The pulley is a uniform disc with a mass of 0.31 kilograms. We already know from the last problem that the I value for a disc-shaped object is 1/2 mass times radius squared. And we want to find the speed of the block after it's fallen through a certain height. So when they're talking about the speed of something after it falls through a certain height, you know, that should alert you it's probably going to be a kinetic energy or a conservation of energy, I should say, problem. Because we've got all UG at the beginning. So initially, I've got all UG. At the end, after it's fallen a certain height, I'm going to call the UG at this point 0. So that'll be my reference point for UG. So the block will now have some kinetic translational energy. And since the pulley has inertia, my system consists of not just my block, but also the pulley. So I have to take into account that the whole system had just gravitational energy at the beginning, but at the end, not only do I have translational kinetic energy of the block, I also have rotational kinetic energy of the pulley. So my conservation of energy equation is going to look like UG to start with. We'll end up with rotational plus translational energy, and then hopefully I can figure out how fast it's going in a translational direction, you know, straight down using this equation. MGH equals 1/2 I omega squared plus 1/2 mv squared, same as in the last problem. I'm going to substitute in v over r, and I'm going to substitute this in for I. So mgh equals 1/2 times 1/2 m r squared times v over r, quantity squared, plus 1/2 mv squared. Again, just as we saw in the last problem, those are going to cancel out. The m's will all cancel out, and I'll get gh equals 1/4 v squared plus 1/2 v squared. So just like the last problem, I will get 4/3 GH. So this is kind of a repeat, same shape as I had before, a disc over here. So it's got the same moment of inertia, but now we actually have numbers we can substitute in instead of just ranking them. I'm going to use 9.81 because it's a mastering physics problem. My height is 0.50. I'll take this offline and calculate that. Okay, I got 2.56, so it says the 2 sig fig, so I'm going to type in 2.6 and submit that. Uh-oh, I better figure out what I did wrong. Let me go back and double check. So you get to see all the ugliness live if I made a mistake. Okay, yeah, I was way too quick to do this. In this step right here, I just caught this. I cannot cancel out. These are not all the same masses here. So I don't know if you guys caught that as you're watching this. This is the mass of the pulley. This is the mass of the block. And this is the mass of the block here. So I just was quickly going through this as if it was the same as the last problem. You cannot cancel those masses out. So, you know, a good lesson that sometimes I'm going too fast and not paying attention to the different masses that are in this problem. So going back to this step right here, the mass of the block times GH equals 1/4 the mass of the pulley times the, I can still have my v squared there, that's still the tangential speed of the pulley, so I can leave that, plus 1/2 mass of the block v squared, because this is translational kinetic energy, that's the block's kinetic energy, this here is the pulley's kinetic energy, so I have to have the mass of the pulley in there. Okay, now let me substitute in some of this information. So the block has a mass of 1.1 kilogram times 9.81. Let me solve first for V, sorry, and then I will substitute in. So I'll do the substitution step last. Okay, so what I did since I had stopped, I rewrote this equation right here with all my r squareds canceled out. I was real careful to keep mass of the block, mass of the pulley, mass of the block in here. I solved for my v squared. So what I did is I factored v squared out of these two terms here, 1/2 mp plus 1/2 mb, and I divided mbgh right here by 1/2 mp plus 1/2 mb. mb being the mass of the block, mp being the mass of the pulley. Take the square root of that side and substitute all my numbers in. I got 2.9 meters per second, and there's your 2.9 meters per second. Now, if you add a small lead weight near the rim of the pulley and repeat it, now you've got a greater moment of inertia for your pulley because you've added to the mass and you've put some mass that's further away from the radius or far away from the radius. So you've increased the moment of inertia of your pulley. So more of that stored UG is going to go towards rotational kinetic energy to get the pulley to start to move. Less of it will go to the translational kinetic energy. So it's the same size pie here, and now on the final side, more of the pie will be dedicated towards getting the wheel to start spinning because your moment of inertia of the wheel is going to go up. So that term goes up. So there's less left over for the translational motion of the block. So it's going to, it says, will the speed of the block increase or decrease? The speed of the block is going to decrease as a result of that. Okay, if you have any questions on that, see me before or after school. We can talk about it or maybe bring it up in class and we'll try to go over it in class. All right, have a great day, guys.